Hi, my name is Christina Quintero, and this is my video lab report for Lab 3, the Black Hole Lab. The purpose of this lab was to model the motion of a star in order to find the mass of a black hole, along with analyzing the involved forces and their changes in momentum. The motion of the star was modeled using v idle and the file of the star's locations given in WebAssign. Using Newton's second law of universal gravitation and the different components of F-net and the change of momentum, the mass of the black hole was determined to be 3.5823 times 10 to the 31st kilograms. The two main principles used in this lab is the momentum principle and Newton's law of universal gravitation. The momentum principle can be derived so that the change in momentum over the change in the time equals the net force acting on the object. Newton's law of universal gravitation states that any two bodies in the universe attract each other with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This can be seen in the equation that is on the slide. The constant g is equal to 6.674 times 10 to the negative 11 Newton meters squares over kilogram squares. In the code, the star's mass, the position of the black hole, and delta t were all given. For this model, delta t is the number of seconds in a day. This line of code indicates where the star data is imported into the code. The first while loop is used to calculate the velocity of the star around the black hole. In the second while loop, v final and v initial are located here. Using this, the star's final and initial momentum can be found by multiplying the star's velocity and mass. From these, delta v and delta p can be calculated. Using our derived principle from before, F-net is set equal to dp dt. Then to find dp dt parallel, p hat is defined as p initial over magnitude of p initial. d magnitude over dt equals the change in magnitude of momentum over delta t. Using these two components, dp dt parallel can be found by multiplying d magnitude p by p hat. This also equals F-net parallel. dp dt perpendicular was found by subtracting dp dt parallel from dp dt to get dp dt perpendicular, which also equals F-net perpendicular. When we run the code, it looks like this. The blue arrow is the perpendicular component of the force, the black arrow is the parallel, and the yellow is the net force. Using the line of code, blackhole.m equals mag F-net times mag star dot position minus black hole dot position to the second over g times star dot m, the mass of the black hole was found. This required the original principle to be rearranged. Mag star dot pos minus black hole dot pos to the second is equal to r to the second in the equation that was originally used. The rest of the equation is known. When the code is ran, the mass of the black hole appears in the print window and has a value of 3.5823 e to the 31 kilograms. For the what does it mean question, according to the momentum principle, these are all equal to each other. dp dt equals F-net, dp dt parallel equals F-net parallel, and dp dt perpendicular equals F-net perpendicular. They differ in the way they are calculated. To find F-net, in this case, we only have to use the gravitational force. However, to find dp dt, changes of the velocity are used. The net force is usually found by a sum of all forces acting on the object, while dp dt is found observing the motion of the object itself. The what-if question, no, the mass of the black hole cannot be calculated if the motion of the stars remain unchanged, along with its data points. There's no alternative gravitational force to calculate a new mass of the black hole. If the motion had been changed and had new points, the new mass could have been calculated. Thank you for watching.